So I created a flow chart that helps you to figure out the type of attractive forces that are involved. So the first question you need to ask yourself is it a covalent molecule, an atom, or an ionic compound? Now, if it's a covalent molecule, you know it's a covalent molecule because you have two nonmetals, okay? Remember, nonmetals are to the right-hand side of your staircase. So if it's a covalent molecule, if the answer is yes, then it can either be polar or nonpolar. If it's polar, it is polar because the dipoles do not cancel. Okay, so we went through this in class. Go back and review that and make sure you're comfortable with polar versus nonpolar. So if the dipoles do not cancel, which is the only explanation you need to give when saying whether something's polar or nonpolar, then the type of attractive force can either be hydrogen bonding or dipole-dipole. It is hydrogen bonding if you have hydrogen and fluorine, oxygen, or nitrogen. And specifically, the molecules have to have a hydrogen that is bound to fluorine, oxygen, or nitrogen. So in some of the example problems we saw, hydrogen was bound to carbon, and then you had a fluorine somewhere else. That doesn't work. It has to be a hydrogen bound to fluorine. Okay? This is the strongest type of intermolecular force. So if you have, for example, HF, hydrofluoric acid, that is polar and it has hydrogen bonding. And so it's going to dissolve very well in water because HF has hydrogen bonding and water has hydrogen bonding. And if you have two molecules that both have the potential to have hydrogen bonding, there's going to be a strong attraction between those molecules. So it doesn't just have to be two molecules that are the same. It can be two different molecules that both have hydrogen bonding. So that's the strongest intermolecular force. If you don't have hydrogen, but your molecule is polar, then you're going to have dipole-dipole attractions. Okay? If instead your covalent molecule is nonpolar, meaning your dipoles cancel, then you're going to have London dispersion forces. So I'm going to go through that in just 1 second. The other way you can have London dispersion forces is if you just have an atom all by itself. I'm not saying a metal. So most of the atoms that exist on the periodic table are metals. Those would have metallic bonding. When I say an atom, I mean a non-metal that's by itself. So for example, neon, argon, any of those atoms would have London dispersion forces. London dispersion forces are your weakest type of intermolecular force. And if I'm comparing two different molecules or two different atoms that both have London dispersion forces, then the one that has more electrons, which you can determine based on which one weighs more, has a larger mass, but we look specifically, we don't talk about mass, we talk about electrons. So the one with more electrons is going to be more polarizable, which means it's going to have a stronger intermolecular force or a stronger LDF. Okay? So when I'm comparing all of these, hydrogen bonding is the strongest, followed by dipole-dipole, followed by London dispersion forces. Now, it is possible for London dispersion forces to be stronger than dipole-dipole forces. If you have a molecule that is extremely large compared to another molecule, and that extremely large molecule only has London dispersion forces, while the other molecule has dipole-dipole forces and London dispersion forces, because remember, every type of molecule or atom has London dispersion forces, then the very large one will have a stronger intermolecular force because the London dispersion forces end up being stronger because that molecule or that atom is so polarizable that it overwhelms the strength of the dipole-dipole forces. So that rarely happens. If you're being asked which will be stronger, as soon as you see dipole-dipole, you can assume that dipole-dipole will be stronger. But if they say, hey, here are your two molecules, this one's stronger, and you look at it and you say, well, it's nonpolar, why would it be stronger than this one, which is polar, which has dipole-dipole forces, then you would know, oh, it's because it has so many electrons, it's so much more polarizable that ends up making its intermolecular attraction stronger. So that's an exception, and they would give you a hint to let you know, hey, this is happening. You don't have to try and figure out when the London dispersion forces could be stronger than the dipole-dipole forces. And the last type of attractive force are for ionic compounds, which are between a metal and a nonmetal. Ionic compounds have a very high melting point. They conduct electricity, but they only conduct electricity when they are in solution. because when they're in solution, their ions are able to move freely. Okay? The attractive force between ions in an ionic compound, that attractive force between ions is called the lattice energy. And the lattice energy is stronger the higher the charge of the ion. So for example, calcium would have a stronger lattice energy than lithium when it forms a compound because it has a 2+ charge versus a 1+ charge. But if the charge is the same, okay, if it's both of them are +1, then the smaller the ion is, the stronger the lattice energy will be. Okay, so higher the charge, stronger the lattice energy will be, or the attractive force will be. If they have the same charge, and only when they have the same charge, then you have to compare the size of the ion. So first look at charge, then look at the size of the ion.